In the previous class, we discussed the interaction of electromagnetic radiation with metals in the bulk and nano sizes. In this class, we are going to discuss some of the photonic applications of metal nanostructures. The metallic nanoparticles and nanoshells produce significant enhancement of electric field near the particle surface under resonant condition. As we have seen in the previous lecture, if we consider a spherical particle of radius a in a uniform static dielectric field along the z direction, this incident field induces a dipole moment inside the nanoparticle. The expression for electric fields inside and outside the particle are given by these expressions. Here n is the unit vector in the direction of point of interest and r is the distance from the center of the spherical particle. The field distribution near a resonant gold or silver nanoparticle looks like this. You can see that the field is strongly localized near the surface of the particle. An interesting feature is that the electric field inside the particle is homogeneous. For metal particles, this is an unexpected result, as we know that electromagnetic fields decay exponentially into metals. Consequently, the quasi-static approximation is only valid for the particle size which is less than the skin depth of the metal given by this expression. Another important point is that the scattered field is identical to the electrostatic field of a dipole located at the center of the sphere. This scattering field is maximum along the direction of the dipole moment vector because of the n dot p time. In addition, it decreases with the third power of distance from the nanoparticle. So the net effect is that just outside the metal nanoparticle, along the direction of the dipole moment, the electric field is strongly enhanced from the incident field amplitude. If excited at resonance, the amplitude of the induced electromagnetic field can exceed the exciting field by many orders of magnitudes. Photonic applications of the metallic nanoparticles are derived from this local field enhancement under resonant condition. Such intense electric field can lead to enhancement of various light-induced linear and nonlinear optical processes within nanoscopic volume of the medium surrounding the nanoparticle. Metallic nanoparticles also exhibit distinct dipole, quadrupole and even higher multipole plasmon resonances depending on their size and shape. Excitation of these resonances create a considerably enhanced local electric field external to the particle. As the particle size increases, the field enhancement reduces with a shift of the plasmon resonance to a longer wavelength. Metal nanoparticles have found numerous applications in photonics. The major features utilized in these applications are the local field enhancement around the surface of a metallic nanostructure, which we have just seen in the previous slide, and the evanescent wave emanating from the surface when exciting a surface plasmon resonance, and the sensitivity of the surface plasmon resonance to the dielectric medium surrounding the metallic nanostructure. The local field enhancement in metal nanoparticles are used in surface enhanced Raman spectroscopy or SERS. You know that the energy spectrum of molecular vibrations can serve as a characteristic fingerprint for the chemical composition of a sample. Due to its sensitivity to molecular vibrations, Raman scattering spectroscopy is a very important tool for the analysis of nanomaterials. Raman scattering can be viewed as a mixing process similar to amplitude modulation used in radio signal transmission. The time harmonic optic field is mixed with the molecular vibrations. This mixing process gives rise to scattered radiation, that is frequency shifted from the incident radiation by an amount that corresponds to the vibrational frequency of the molecules. The vibrational frequencies originate from the oscillations between the constituent atoms of the molecules, and as we had seen in the harmonic oscillator problem in quantum mechanics, these oscillations persist even at 0 Kelvin. Since the vibrations depend on the particular molecular structure, the vibrational spectrum constitutes a characteristic fingerprint of a molecule. This figure shows the energy level diagrams for the Stokes and the anti-Stokes Raman scattering. And this one is the experimentally measured Raman spectrum of rhodamine 6G. Raman scattering is an extremely weak effect. The Raman scattering cross-section is typically tens of orders magnitude smaller than the fluorescence cross-section of most molecules. The field enhancement associated with the surface plasmons has been extensively explored for increasing the interaction strength between the molecule and the exciting radiation. The most prominent example is the surface enhanced Raman scattering. The enhancement is large enough to observe Raman spectra even from a single molecule. Now let's discuss some other applications utilizing the local field enhancement of metal nanoparticles. While discussing the near field optics in the second module, we had seen that metallic nanoparticles or metal tips with the nanoscale dimensions could be used to enhance the field in the neighboring nanoscopic region in apertureless near field microscopy and spectroscopy. The local field enhancement also contributes to the enhancement of the linear and nonlinear optical transitions in molecules within nanoscopic distance from a metallic nanostructure. Similar to SIRS, the fluorescence of an emitter in the proximity of metal nanostructures can be enhanced as well. Fluorescence here results from the excitation of the emitter by the incident field, which can show significant enhancement due to the plasmon resonance in the metal particle. Now let's discuss some applications utilizing the evanescent wave excitation. When light is coupled as a surface plasmon excitation in a metallic film or a nanostructure, it produces an evanescent electromagnetic field emanating from the surface and exponentially decaying into the surrounding dielectric field. This evanescent wave can be utilized to preferentially excite an optical transition in fluorescent molecules or fluorescent nanospheres near the surface of metallic nanostructures. Evanescent wave excitation has been utilized in various fluorescence-based optical sensors. It has also been utilized to convert a propagating plasmon wave in a plasmon waveguide to a fluorescent optical signal. The light emerging from the tip of a tapered fiber of a near field microscope locally excites the plasmon oscillations. The light wave is thus converts into electromagnetic energy in the form of plasmon oscillations, and it is transported through the array of metallic nanoparticles. And this guided electromagnetic energy can excite a dye in the guided path. The resulting fluorescence can be collected in the far field. The surface plasmon resonance frequency and its width are both sensitive to the surrounding dielectric medium, and this sensitivity forms the basis for the detection of biological analytes which can bind to the surface of metallic nanostructures through a typical antigen antibody coupling, which changes the dielectric constant and which results a corresponding shift in the reflected spectrum.